student, this is lecture 25 based on second unit for digital signal processing. And in this lecture, we are going to discuss about your design of digital Chebyshev filter. Okay, because in last lecture we have been discuss about this IIR Butterworth. Okay, so but in this lecture we are going to discuss about this Chebyshev IIR filter. Okay, so let's start with this some basic concept about this Chebyshev filter. Okay, so just give me 1 minute. Okay, so there are some points over here. We are going to discuss firstly magnitude response, order, Chebyshev polynomial, and design procedure. So let's discuss about the Chebyshev low pass filter has magnitude response, and the response function is given by this equation, that is equation number 1, where mod of h j ohm equal to a upon 1 plus epsilon square cn square ohm upon ohm c to the power 0.5 is under root. Okay, where a is your filter gain, epsilon is a constant designing parameter, epsilon c is the 3 dB cutoff frequency. Okay, and cn ohm upon ohm c is the Chebyshev polynomial. Okay, and where this n is the your nth order Chebyshev polynomial, and this Cn is given by this these two equation for when the mod x less than equal to 1 and mod x greater than equal to 1. So for mod x less than equal to 1, Cn x equal to cos and cos inverse x, and for mod x greater than equal to 1, cos h and cos h inverse x. So you have to remember these two equation also. Okay, now the magnitude response has equiripple passband and maximally stop band. Okay, so it has equiripple passband and maximally stop band. Now, if we talk about the designing parameter, so the design parameters of Chebyshev filter are obtained by considering the low pass filter with the desired specification as. Okay, so again we are considering the low pass filter, and that is given by delta 1 less than equal to not h is e to the power j omega less than equal to 1, where omega is lying between the 0 and omega, and h mod of h e j omega less than equal to delta 2, where omega is lying between the omega 2 to pi. Okay, now uh, most of the time we have considered this a equal to 1 if it is not given in the question, so always consider the unity gain. Okay, so gain of the filter is 1. Now we know the uh, value of this function. Okay, so we have seen in this equation first. Okay, so just put this value in this equation 2. Okay, so when you put the this value, we will get this del 1 square less than equal to the function which we have discussed in equation number 1, 1 upon 1 plus epsilon square cn square ohm 1 upon ohm c less than equal to 1, and for this equation 1 upon epsilon square cn square ohm 2 upon ohm 1 ohm 2 upon ohm c less than equal to del 2 square. Okay, so we will get this equation 3 and equation 4. So most of the time in question, okay, we have to compare the given equation with these equations. Okay, 3 and 4 and from the equation 2. Okay, for finding out the value of delta 1 and delta 2. Anyway, assuming ohms equal to ohm 1, if we consider ohms equal to 1, then Cn ohm 2 जो आपका था ohm 1 upon ohm c, that is equivalent to ohm c upon ohm c, that is Cn1. This is always equal to 1. Okay. Now from the equation 3, okay, we can easily, now we know the value of this Cn equal to 1. So del 1 equal to simply 1 upon 1 plus epsilon square, because this value will be 1. Okay. Now from this equation we can find out the value of the epsilon. Okay. So epsilon equal to 1 upon del 1 square minus 1 to the power 0.5. Okay. Important equation for calculating the epsilon. Okay. Now for the order of the filter from equation 4, now we can assume ohms equal to ohm 1. Okay. So that is Cn. Okay. If we talk about this equation number 4. Okay. Now equation number 4, we have to calculate the ohm 2 upon ohm c. Okay. So now if ohm c equal to ohm 1, that is ohm 2 upon ohm 1, that is given by greater than equal to 1 upon del t square minus 1 to the power 0.5 into 1 upon epsilon. Okay. Now since ohm 2 greater than ohm 1, so we can easily write it down in terms of from the equation 2. Okay. Sorry, equation this Cn. Okay. So that will be cos h and cos h inverse ohm 2 upon 1 greater than equal to simple value 1 upon epsilon upon 1 upon del 2 square minus 1 to the power 0.5. Now from this equation we can calculate the value of this n, because for any filter the first thing we have to calculate the order of the filter. So n, from this equation we can easily calculate the value of the n, that is n greater than equal to cos h inverse 1 upon epsilon multiply with 1 upon del 2 square minus 1 to the power 0.5 divided by cos h inverse ohm 2 upon ohm. Okay. So again the same thing is here, but we have done in Butterworth. The value of n chosen to the next closer integer. So suppose you are getting 3.7, you have to choose the 4. Okay. So because closer next value is 4 integer value. Okay. And the value of the ohm 1 and ohm 2 are obtained using the bilinear transform or impulse invariant transform method, whatever is given in your question. Okay, so we can use both the method for calculating the value of ohm 1 and ohm 2. Okay, now the transfer function, generalized transfer function, okay, for analog filter is calculated as Hs equal to k equal to 1 to n by 2 product of dk ohm c square upon s square plus bk ohm cs plus ck ohm c square when n is even, means if we have n equal to 2, 4, 6, then you have to write this Hs. If n is odd, okay, then obviously you have to write v naught upon v naught into ohm c upon s plus c naught into ohm c k equal to 1 to n minus 1 by 2 product of Vk ohm c square upon s square plus Vk ohm c s plus Ck ohm c square. Okay, where the Vk value is given by 2 by n sine 2k minus 1 pi upon 2n, and Ck is given by n square plus cos square 2k minus 1 pi upon 2n, and c naught equal to y. Okay, so for calculating this transfer function, you have to know the value of capital Bk, small ck. Okay, so small bk, small ck is calculated by these two equations, where yn equal to because you are using yn. So the parameter yn is given by 1 by 2 in bracket 1 upon epsilon square plus 1 to the power 0.5 plus 1 upon epsilon to the power 1 by n minus times 1 upon epsilon square plus 1 to the power 0.5 plus 1 upon epsilon whole power minus 1 by n. So one time plus 1 by n, second time minus 1 by n. So from this yn will be calculated, and yn we will put yn over here in this equation. Okay, so when we put in this equation, we will get the value of bk and ck. Now the last parameter is remaining is capital bk. Okay, so for calculating capital bk, we use this formula, that is a upon 1 plus epsilon square to the power 0.5 equal to k equal to 1 to n by 2 product of pk by ck for when the n is even. When n is odd, a equal to given by k equal to 0 to n minus 1 by 2 product of bk by ck. Okay, so when all the parameters b, capital bk, small bk, ck, ohm1, ohm2, ohm6 calculated, we can easily calculate the value of the Hs. Now, after obtaining Hs, the system function of digital filter is obtained from Hs, okay, using the specified transformation technique, that is, it can be bilinear transform or it can be impulse invariant. Okay, so this is the whole process for calculating the Hs. Okay, but you have to remember, it will be mentioned in question whether you have to use BLT, bilinear transform, or impulse invariance transform. Okay, so this is all about your lecture 25, basic steps for designing the transfer function or designing the your Chebyshev filter. Okay, so thank you, students.